We now need to consider sampling rate or sampling frequency. You'll understand, as for sampling resolution, that how often you need to make the measurement equally depends on what type of measurement it is you're making. For example, a patient under observation after a routine operation, it may be sufficient to record their temperature once an hour. However, in intensive care, it will be more common to record it once every 15 minutes. We need to understand how fast the measurement is likely to change and make sure that we make the measurement often enough so that important changes aren't missed. On the left side of the screen is the signal coming from the signal generator as earlier. On the right of the screen is the signal that has artificially been resampled at too low a sampling rate. This also gives a stepped appearance to the waveform, but this time it's because we're sampling the waveform too slowly, and so we don't know what happens between the times at which we take the samples. I'm going to turn the sound on in a moment, and the difference will become apparent as I increase the frequency of the signal on the input to the analog to digital converter. As I increase the frequency of the signal from the signal generator, the pitch initially rose, but beyond a certain point the pitch began to fall again until we reached the position we're at now, where although the input waveform is at a high frequency, the output doesn't appear to be changing at all. Here's a sine wave that we would like to sample. Ideally, we would take lots of samples for each complete cycle of the waveform. In that case, the blue dots would give a faithful reproduction of the original signal. If we sample less regularly, then the signal will have changed more in between our sampling points. And in fact, if we sampled too slowly, then the waveform could have done an entire cycle in between two samples, and so we would never know it had changed at all. That's indicated by the blue crosses and is exactly what we've seen in the demonstration. This problem, whereby sampling too slowly you can completely misinterpret a fast-changing signal, is known as aliasing. Just looking at the problem on the board, you might expect you would have to sample at least twice on each full cycle of the waveform in order to get some impression of how quickly it's changing. And in fact, there is a mathematical proof of this called Nyquist's sampling criterion, which says you must sample at least twice as fast as the fastest frequency component in the signal you're recording. Preferably, you would sample even faster still, but as an absolute minimum, you must sample at least that fast, else your signal will be irreversibly distorted. Well, that was aliasing on a manufactured signal, but this demonstration wouldn't be complete without a little more assistance from Green Onions. For me, the most interesting thing about this demonstration is just how good the human ear and the human brain are at picking out the music from what appears to be a hopelessly distorted waveform.